We are very happy to have our own team to tell us about bootstrapping reason.
Thanks for the opportunity to speak. I'll tell you about a paper that we just posted yesterday, and about the good old Ising model. These days, when Bootstrap are talking about the Ising model, we really think about the CFT, but here we're going to study the Lattice version. The methodology is along the lines what I call the Lattice/matrix bootstrap, and there have been a number of important papers on the subject. First, this in known to our community by Anderson and Krzyzewski as an attempt to put bootstrap bounds on lattice gauge theory, pure amulus in 2016, and then that inspired the work of Henry Lin, the so-called matrix bootstrap in 2020, and which then further inspired the work of Kazakov and Joan from earlier this year. I should also mention that the same methodology, just in the classical limits, was also investigated unknown to most of us by Galuskin and collaborators since 2015. This is for classical dynamical systems, and it's on the Math DS archive, and most of us don't usually look at it. It's really the same, just the classical limit of it. Okay, so let me, and I understand that there will be, Zentran is supposed to discuss this, their work on the Yamil's version of it next week, assuming he recovers from COVID, I guess.
He's here already.
He's here already, great.
Yeah.
This talk will be, we'll discuss some things that are very specific to the Ising model, and this should be more or less self-contained. Let me start with the model. So we're talking about the good old statistical Ising model. Ensemble of spins on a lattice. This lattice is the Euclidean space-time lattice. From the point of view of in the field theory point of view, here we're just going to be talking about a statistical ensemble of spins over this lattice. Let's say d-dimensional Ising model will be defined, let's say, along the partition function by sum over the spins. Let's say spin variables, we take it to be plus minus 1 s of x. So in my notation, x will be a site on the lattice lambda. Sx is a spin variable, takes value plus or minus 1, and weighted by e to the minus, usually write beta h. I'm just going to set beta to 1 for the sake of the discussion. I'll absorb the inverse temperature into the coupling and magnetic field. So we're at J, some nearest neighbor, neighboring sites, x and y, Sx, xy, plus h, sum over the lattice sites, x, where h is the external magnetic field, J is the coupling, and throughout this talk, I'll focus my attention on the ferromagnetic Ising model, so I'm going to assume that J is non-negative. And of course, the sign of H doesn't matter. You can flip the overall sign by a Z2 symmetry that flip all the spins. And of course, the observables of interest are going to be thermal expectation values of products of spins. So something like this, where I'm going to use a shorthand notation. So observables. Where when I write underline S subscript A, this means so A is going to be a subset of the lattice, a finite subset typically. So A is some A is some finite subset of the lattice. I take the product of all the sides in A, S of X. So for example, so suppose I have a 2D square lattice, and I can can take A to be a set of some points and study query functions in space. These are the most basic observables one can study, and this will be, of course, defined as the 1 over z times this sum with the insertion of this and the usual the weighting factor. Okay. So now the method. Forget the method. Let me just say that, of course, as is well known, there are two cases of primary interest: the 2D and 3D lattice. So in 2D, you can consider lattice of different shapes, but I'm gonna for this discussion, I'll restrict our attention to just the usual square lattice in 2D and the cubic lattice in 3D. In 2D, well, in both 2D and 3D, we know that there's a phase diagram that looks like this, where there's some critical value of the coupling, usually referred to in terms of temperature, but I've absorbed the temperature into my definition of J and H. So I just talk about the critical value of the coupling. Let's call it JC. There's a inverse phase transition over here, this is the low temperature phase, and field theorists are usually interested in the neighborhood of this point, where long distance correlators are described by a continuum quantum field theory that can be viewed as the CFD perturbed by two relevant operators. In this talk, we're going to be interested in observables like this. We'll focus on the simplest kind of observables, 1 or 2 speeds, the correlation function, exploring this JH plane. And not surprisingly, as one might expect, things will get most tricky near the critical point, but we'll see what kind of results obtain. Any questions about the setup before I describe the technique? Okay, so now let me describe the method, which is very, very general. It applies to, and you see, it'll be very general. It can, it can be applied to lots of systems on the lattice, or not even a lattice, and it applies to things like statistical expression value, or even time averages of a classical dynamic system. The ingredients are the following. So first of all, we'll see that there are some basic identities relating these observables among one another. Now, of course, there are some lattice symmetry. So, obviously, there's a rotation, translation, rotation by 90 degree, reflection, translation, symmetry. So this observable only depends on this subset A up to these symmetries. Beyond that, they are what I would call the spin flip identities or equations. This is the same as what one would call the perhaps the Schringer Dyson equation or loop equation in related contexts. In this case, I'll just describe these identities specialized to the Ising model. They're very easy to derive. They're very simple. They have been known for a long time. Actually, let me describe that in a second. Let me just say that the ingredients in doing the bootstrap will be some identities relating these observables, the spin expression values, in this context. Unlike the loop equation for Yang-Mills theory, here this spin flip identities that I'll discuss are going to be linear relations among these spin expression values. And then there will be some positivity conditions And there are several different types of positivity conditions. I'll discuss them in some detail. But let me first describe the Smith-Flip identities. So right here. This is very simple. So suppose I study this equation value given by like a formula. So let me just write it out. Let me say I'll sum over. In fact, let me omit the. Okay, let me include this minute. So here I'm summing over all these spin variables. So we can consider change a variable. Sz to minus itself, where z is some site. It's for a given site z in the lattice. Now there are two cases to consider. So either z is not in the subset A of the spins I'm computing the expression value of, or z is in the subset A. Well, in this case, obviously, flipping the spin variable as z doesn't touch this correlator. But on the right-hand side, you're just gonna, the effect of that is just gonna, you're gonna flip the signs of some of the terms here. So it's easy to see that the effect of that is you get a correlator of e to the minus 2j times the sum over sz times sx, where x is adjacent to z, and then minus 2h s that. Similarly, if z is equal, if the size z lies in subset A, then you have the minus on the left-hand side equal to the same thing. Now, this factor comes from flipping the sign of a few terms in the infinite sum, but it's just a finite set of terms. In fact, here, as you can see, if there's a site in z, then the only thing that's involved, the only spin variables that are involved in this exponent here are the sites adjacent to z. So this is the exponential of a linear combination of the some product of a finite set of spins, and the spin take value plus minus 1, so you can just expand it. You can just sum up the exponentiation and write this as some polynomial expression in this case.
In the second case, what happens if you flip the spin which sits inside SA under the summation sign? You flip this. I don't understand why you.
I mean, let me see. On the maybe you'd be happy if I put the minus sign over here.
Maybe I'll be
Anyway, is that your formula?
Thanks.
Yeah. Okay. So all right. So anyway, you can expand this out. It's not a very difficult exercise. But of course, this knows about all the details of the lattice. When you expand this out, you can write this right-hand side as a finitely many terms involving SA as a linear combination of SA times some additional insertion of spin. The point is that first of all, there are finitely many terms. Second of all, the coefficients are some polynomials in terms of cosh and sinh of j. Not surprising.
A question. You're also summing like 1 over z also includes the sum over, like that z term includes the sum over spins. Are you flipping SA like sz also in that? Or
this is just some fixed number, so right? This doesn't affect the discussion here. I'm fixing the coupling and magnetic field, of course, in this discussion. So this Z is some function, function generation. I mean, of course, strictly speaking, this is supposed to be viewed as a limit that is supposed to cut off the lattice in finite size, take a limit, otherwise it's zero. Diverge depends on how you define it, but it's the usual.
Okay.
Just to make sure I understand, so on the right-hand side there, that if SA was an endpoint function, then the right-hand side will at most be, it'll be a linear combination of things at most n.4 and n plus 4, n plus 6 insertions, is that right? Where 4 is like the...
That's correct. That's correct, because you know, in the case of square lattice, you only have this these other 4 independent spins, and of course each thing it's 1. So if you square it, you just get 1. Yeah. All right. So in practice, we are going to focus on a finite domain, finite region on the lattice, and inspect all the possible spin insertions in that domain, and such identities that relate Fourier functions of spin insertions in that domain. So, for example, on the square lattice, you might consider a domain like this. So I'll refer to this as a 1-3-1 diamond. It's a diamond-shaped thing with 1 point, 3 point, and 1 point. And later I'll consider a bigger diamond, like 1-3-5-3-1, something like that. So on this domain, we're going to consider all possible spin insertions on these points. Of course, in this case, you have 5 points, so that's 2 to the 5 inserts, other spin insertions. And then you can study, you can consider these spin flip identities that close within the set of spin correlators. And if you stare at this relation, you see that the only way for that to close is if you choose this point to be Z. Because then this right-hand side only involves these other neighboring spins, but they close within the set, never takes you outside of this 1-3-1 diamond region. Generally, if you have to consider a bigger region, in order to maximally utilize these spin flip identities, you want to be such that you can kind of consider this sort of padded region where, for example, bigger picture. So, for example, you consider something like this. I guess this one, we call this 1-3-5-3-1 diamond. So for this, now you can take Z to be another color. You can take Z to be this point, this point, this point, this point, and this point. If you flip the spin in either one of these yellow cross points, the right-hand side still involve only spin insertions within this 1-3-5-3-1 diamond, and these identities will close among themselves. Okay, so these are a basic set of linear relations, and then there's a ton of them. These relations actually, even though they're linear, that sounds very simple, they're actually very non-trivial in the following sense. If you collect all these linear identities on all the possible spin insertions within this domain, you'll find that it is a grossly, excessively over-complete linear system of equations. So most of them are not independent. But it's not obvious which ones are independent, and I'll come to that later. Eventually, for a larger system like this 1-3-5-3-1 diamond, so far we can only handle it numerically. And to solve the relations, it's a bit tricky when this linear system of equations are over-complete. You have to worry about numerical stability issues. I'll come to that in more detail in a moment. So these are the analog of the loop equations. So it's just linear relations among the spin coordinate functions.
Chief, you said over-complete, but they don't determine everything.
No, they don't determine, of course. I mean, you saw
redundant. Like the linear identities between
Yeah, there's a lot of them are redundant. That's the thing. But this redundancy occurs in yeah, but it's not obvious. You know, which ones are redundant are not obvious to the extent we know.
Because I guess you also have to model out by the symmetries, right? If you take
Yeah,
the
yes,
points
yes, that's
function.
right. Later, I'll show a chart of some examples how many redundant equations versus dependent equations there are.
Sorry, you said the set of relations is obtained by picking different S bar A, and for each of them choosing the point Z inside the time.
That's right. That's right. But you see that on the right side it involves many other combinations.
Quick question. I know you already have enough equations, but are there in principle more spin flip identities that you could derive by taking 2 points Z1 and Z2 and doing an analogous thing?
I don't think they will be independent, right? Because you can just always flip one at a time, and the others will be consequence of that. So
okay.
I don't think they will be independent. In fact, in some severe cases, when you said magnetic field is zero, it was known that in the 2D case there are other, maybe not surprisingly, in the 2D case with the zero magnetic field is integrable, but there are other nonlinear relations amongst these values. But I would assume that they are consequences of these linear relations. No, I don't know. Or certainly something right. Okay. So anyway, so you have these identities, and next let me discuss the positivity constraints. So positivity conditions. Now, a priori, you might just want to put in as many known positivity conditions as you'd like. And there are 3 types of positivity conditions that I'm aware of for this system.
Sorry, just a basic question. So there you were distinguishing whether Z was in A or not, but
yeah, so I didn't say what A is, right? This region is not A. This region, let me give it a name. Let me call it D. All right, so I'm going to be considering A that sits inside D. So D is a region where I'm only going to be, I'm only going to consider the set of correlators with the spin, inserted in this region.
Okay.
But where I insert, that's up to you, right? I want you to scan over all possible choices.
Okay.
So A could be like these 3 points. Okay. There are 3 types of positivity conditions I'm aware of. The first one is what I would call the reflection positivity. Now, this is, let me just say, coming from quantum field theory, of course, one expects that if you had a Poincare invariant local Euclidean quantum field theory, expect unitary, you expect that correlators or local operators, something coming to local operators inserted on one half of the Euclidean space-time is together with so some operator O here and some reflected operator OR, and then you expect O reflected to be non-negative. Now, on the lattice, first of all, it's not entirely obvious, but you have to say what precisely you mean by reflection. First of all, you presumably want to consider reflection, or that takes the lattice to itself. But then you still have to prove that this reflection positivity actually holds for the model we're talking about. It turns out that okay, let me describe the kind of reflection you can have on the lattice. Let's say we fix the origin here, you can pick some lattice vector, let's say some lattice vector v, and you consider reflection in the direction of v. Suppose you consider that. What would the reflection map look like? It will take a lattice side x to something like x minus 2v dot x over v squared v, something like this. but not anything goes because you have to map lattice to itself. Without lots of generality, you can assume that V is a primitive lattice vector in the sense that it's not a multiple of any other lattice vector. So this is, for example, this 1,1 vector is a primitive lattice vector on the square lattice. Now, if V is a primitive lattice vector, you have an expression like this, x is some other lattice vector, you can always find x such that v dot x is equal to 1. So then you need this 2 over v squared to be an integer for this to lie in the lattice. For that purpose, this v squared can only be either 1 or 2. So there's no other choices. So that seems to be a bit restrictive, but it's okay. So these are actually the only type of reflection I know of. And you can, there's a slight variant of this where you shift this by a constant c, let's call it v, where this constant c, once again, for this to be to lie in the lattice, the c has to be an integer multiple of v squared over 2. That is, in the case of v squared equal to 1, for example, if you reflect in this direction, the c can be a half integer, but otherwise, reflecting in this direction, in the diagonal direction, then c would have to be integer. And if you play with this for a minute, you'll recognize that essentially there are only 3 types of distinct inequivalent reflections. Even though I'm drawing the picture for the square lattice, but the story is basically the same for a cubic lattice or high dimension, hypercube lattice. You can really only take the v to be either along this to the adjacent sides or in this 1,1 direction, and there isn't something like you might imagine in a 3-dimensional lattice you can reflect in the 1,1 direction, but as far as I know, there's no such reflection positivity condition I can derive.
Sorry, for the existence of a transfer matrix, is it also a requirement that the system be positive under this generalized notion of reflection that has this?
The existence of a transfer matrix. Why do you want that?
Well, this is, people always say this is connected to the notion of reflection positivity.
So I'm not aware of, I'm not sure what that refers to.
Well, that's the simplest way to prove that the lattice theory is reflection positive. You have to show that the transfer matrix is Hermitian.
I guess I don't know the definition of the transfer matrix here, but this is not very hard to prove. In fact, first of all, these are, what I'm about to describe surely was known, but it's the proof like 1 or 2 lines.
And maybe it takes the secret that relies on this transfer matrix, but okay.
If you know some generalization of reflection positivity beyond what I'm about to describe, I'll be happy to know, but anyway,
I was just thinking this might already be more general than what I knew.
Anyway, let me just write it down. It's more or less the most obvious thing you can imagine.
So in the continuum model, reflection positivity holds respect to any direction.
Right.
And then to get to the lattice, we are deforming by some operator with the spin, and you're saying some of these directions then are not reflection positive anymore. How does that reflection positivity break?
I don't think I'm in a position to answer that right now. But maybe toward the end, we'll have something more intelligent to say. But right now, I have nothing to say. Okay, so let me just describe the 3 types of reflections. One type is that I'll just illustrate it with a square lattice example, but as I mentioned earlier, there's really nothing new for the cubic as far as I know. So you can reflect, horizontally, let's say. Of course, vertically is the same thing, by rotation by 90 degrees. So you can reflect horizontally where the fixed line is along an array of sides. There's another kind of reflection you can do in the same direction. So this corresponds to the case where this v vector is just a unit vector in one direction, and c would be equal to 0. So there's no shift, it's constant c. But you can also consider a case where c equals 1/2, in which case you reflect in this way. Right? These are different. And then there's diagonal reflection where it just reflects. Oops. I'm not doing this very well, but anyway, you reflect along this diagonal line. In this case, the shift actually doesn't declare so equivalent reflection. Now, to prove this, now I should say that when I say reflection positivity, I'm allowing O to be a linear combination of these spin insertions on one side with some coefficient T, A, where A sits in the half of the lattice. Let's say this is the half of the lattice, which we call H. So that H includes the mirror plane, or in this case, the mirror line itself. And it's not very hard to prove this. In the first case, essentially, the insertion of O on the right-hand side and OR on the left-hand side, insertion of O on the right-hand side produce for you a, if you wish, a wave functional. That's a function of the spins on all the sides along the mirror line, and the left-hand side produces another one, and the whole Fourier function is a sum of some square of some quantity that is manifestly non-negative. Similarly here, this case is actually less obvious because you're cutting the links. But you can prove this reflection positivity in this case, assuming that it's ferromagnetic. So that's kind of interesting. I don't know whether it's true for the anti-ferromagnetic Ising model, but we're not considering that because we're interested in this is a sign that includes the critical points, so we're going to be interested in this model, this version, the ferromagnetic version. But anyway, in any case, this can be proven basically by starting with a finite version of the lattice. You just take this, you take the e to the j of the spin on the left and the right of the link, and you just expand this exponential, and you can show that term by term is positive, and the whole thing is positive, and you take the limit of the lattice to infinity, and it's positive. Yes?
I think it's obviously not true in the antiferromagnetic case, right? Because
Okay.
you have negative expectation value across for two spins across a bond like that.
Yeah, I guess.
Nearest neighbors.
Yeah. Right. Good.
Hey, are you working in thermodynamic limit, so it doesn't matter where the reflection plane is?
I am going to take the thermodynamic limit. So the results I'm going to discuss, I will soon assume translation symmetry. So for that purpose, it doesn't matter where I reflect. However, I am going to restrict myself to a region, to a domain. So once I do that, I do have to restrict myself to reflection positivity relations that involve only operators within that domain. So for example, in the case of this 131 diamond, if I can verify that if I reflect along here versus reflecting along here, actually the relations are slightly different. But we'll take into account of all of them as long as the only operators can find in this region. Okay, so that's reflection positivity. Next, we're going to discuss some other types of positivity or just inequalities. Well, this one is the most evident one from the continuum quantum filter point of view. There's also something which we call square positivity. So this is something that's very simple. It just says that any operator squared is square value is negative. And I'm talking about this operator O. I mean a linear combination of these SAs with the real coefficients. Now this is of course obvious, but despite that it's obvious, I'm not aware of a field theoretic analog of this. So from the continuum quantum field theory point of view, this is a bit weird, and in fact, it will turn out I don't have we don't have a deep understanding of this, but in all the examples we have inspected for regions like this, it turns out that at the end of the day, the square positivity relation appear to be redundant. So in all the examples we have checked, the reflection positivity together with the speed flip identities actually imply the square positivity. And so So even though these are something more or less obvious, but it turns out that they will not be needed. I should say nonetheless that just because some positive relations are redundant doesn't mean that you necessarily just want to throw them away, because sometimes for some different programming, as we'll come to shortly, I was told that having redundant input sometimes can improve the efficiency of the sort of convergence of in finding the optimal bound in solving an SDP problem. Then there's a third type of positivity conditions. These are the have been known for a long time, so-called Griffith inequalities. There are two basic types of Griffith inequalities that will be relevant for the discussion here. I'll call them, I'll call them the first and second Griffith inequalities.
Can I ask a question about the second one? If you take, say, not squared by the fourth power and so on, is this redundant?
Yeah, but I mean, this is always an arbitrary combination of a product of arbitrary spins.
Oh, okay.
Yeah, so this S underline always refers to arbitrary product of spins. But a single part is like a monomial in this case. It's like a moment. So the first Griffith, so these are, I should say importantly, these apply to again assume J is the negative. I'm also going to assume that H is a negative. Of course, the second I'm free to assume without loss of generality. So the first Griffith inequality says that every moment is non-negative. It's not surprising to have a single spin, but if my field is positive, it's positive. It's going to be positive, but it's true for all moments. And the second says that if you have SA, SB for two subsets A and B, this is greater than or equal to SA, SB, express value separately and take the power. For example, this one in particular will imply one simple consequence of that is in the case of the ferromagnetic Ising model, typically these exponential values are going to be monotonic functions of J and H. So if you make a plot of the spin coordinator as a function of J, it's going to be monotonic. That's the consequence of the second Griffith inequality. So then anyway, the proof of these are standard, but we briefly reviewed this in the paper. Yeah.
The A and B have to be disjoint and G2 or not?
I don't think so. I don't believe they have to be disjoint. Okay. Now, it's perhaps already evident that if you expand all these positive conditions on the basis, so all of these are some positive condition of some linear combination of these moments. It's more or less evident that at least the 1 and 2, the reverse positivity and the square positivity can be expressed as the semi-definite positive, the positive semi-definiteness condition of some matrix whose entries are linear in these moments.
I think they need to be disjoint, otherwise the relation will not make sense.
Sorry?
I think they would need to be disjoint, right? Otherwise I can...
Which one?
The last one. G.
No, I was talking about the first two, not the last one yet. I'm saying these two can be written as positive semi-definite.
No, I was thinking about Max's question, about G2. I
G2.
think A and B need to be disjoint, right? Otherwise I can always multiply by a product of Sx squared, which is 1 on the left-hand
yes,
side.
and the right-hand side is less than 1, right?
So I can enhance A by adding a bunch of spins, and B by adding the same amount of spins, and then I would conclude.
Why is that the problem? I don't think that contradicts anything.
Really? Okay.
Yeah, I don't think that contradicts anything. Yeah, I don't think that's required.
Sorry.
And in fact, for example, in particular, it implies that all the exponent value is less than or equal to 1. Of course, that's true. For example.
Sorry. You may have mentioned it, but how about the DOM identity like SA less than 1?
Well, I was just saying, but SA less than 1 is a consequence of
on
this.
that.
Right, yeah, I think here the A and B can overlap.
I see. There are some of these trivial things that follow from the spin thing plus or minus 1. Like if you take 3 spins and then you look at the sum of pairs like XY plus XZ plus YZ, things like that have a range that's a bit smaller than you think.
So
there are constraints like that.
yeah, I mean, there could well be higher inequalities. In fact, one place I learned this from is the book of Glim and Jaffe that had discussed, there's a chapter discussed the Ising inequalities. In that book, they discuss some higher version of Griffith inequality. But that higher version of Griffith inequality only applies to something like, not for just the plus minus 1 spin, but for the some phi-4 potential and some generalization of that. And as far as I can tell, that doesn't, the way that was written in the book doesn't directly apply to the plus minus 1 spin Ising model. But I wouldn't be surprised if there's some higher version of that. But as you'll see later, so one of at least the conjectural statement I'm going to make is that this reflected quality is more or less enough by itself. These will help improve the bound, but they are probably not actually logically necessary. The bound might converge without impulsiveness. Okay, any other questions? Let me see. So, I think at this point I'll probably switch to slide. Let me see. Right. Maybe maybe I won't even write this down. But as I said, sorry, I didn't finish the comment I was about to make. I was saying, so this first two can be formulated as the positive semi-definiteness of some matrix. So there's some Mij that is positive semi-definite, and each entry of this matrix is some over these spin is a near combination of these moments, of the spin coordinate. Once if you formulate this positive condition in this way, then I can then we also have further linear relation among these. So what we can do is that you simply first you solve these linear relations, the spin flip identities, and then you get these matrices which are positive semi-definite, whose entries are linear in the independent variables, and then you can choose to minimize or maximize some linear combination of that. Yes?
Wait, are we summing over all A's that are a subset of the lattice, or just some choice of?
So for the discussion, I'm only going to restrict to those where the A actually lies in the domain D. Maybe I should write this A inside the domain D. The D is of my choice. Of course, the bigger the better, but then there's a computational limit. I will describe what the status we have arrived at so far. Let me mention that for the Griffith inequalities, this one is obvious. They can write as positive semi-definiteness of a 1-by-1 matrix. This one is not so clear. This one is not, generally speaking, I don't know how to write this as a positive semi-definiteness of a matrix. You could relax it a little bit and write this, write a weaker version of this condition as a positive semi-definiteness of a matrix, but generally I don't know how to do that. Except in a situation where if B is related to A by a symmetry, like G, where G is the automorphism of a lattice, if B is related to A by a symmetry, then this can be written as a positive semi-definiteness of a 2-by-2 matrix. So that's what we can do. But when the B is not, so in this case, it's we'll have a STP problem. In the second case, it's I don't know how to do that in general. Anyway, but the consequences of this we'll discuss momentarily. Okay, so anyway, so the strategy should be now clear. So once we have these positivity conditions, we're going to solve these linear relations, and then we'll minimize or maximize the bounds. And the hope, of course, is that these bounds will converge eventually as we make this domain D bigger and bigger. They'll converge to the hopefully the actual answer. And we want to explore whether that is true. Of course, even if it is true, there's an important question of, numerical efficiency. How fast does this converge? So I guess now I will switch to slides. Do I just all right. So here's there are many such spin flip identities. Here's one of them. This is here I'm just showing a picture of a three-dimensional example for I think this will be the simplest domain, which is, in the 3D will be the 151 diamond, which I think I will. Let me just draw a picture here. So in 3D, you can say. So going down, so you have this thing which is called the 151 diamond. So on that, you can write down a bunch of this split flip identities. Here's one of them, where it may not be totally easy to see, but each of these box represents the expression value of a number of spin insertions in the black dot locations inside this box, and there's some coefficients, and these A's and B coefficients. These are functions of J. This is in the case of zero magnetic field. You can also derive analogous equations with magnetic field. This is in the three-dimensional case. This is just a typical example of what they look like. So I guess I've shown this picture earlier. So in 2D, do I have the stick? Something I can point it. Yes. Maybe not. That's okay. So in 2D, the simplest non-trivial region you can consider is this 131 diamond, which I showed earlier, and then you consider this 13531 diamond. And the 13531 diamond is the biggest region we have considered in 2D. And the bottom, this is an illustration of the three types of reflection positivity we can have, where these blue and green dots represent the possible location. Just some random example of the possible location the spin you can insert. In particular, they can be inserted on the mirror reflection line itself.
Can I ask something, Sheik? Is there something particularly nice about diamonds? Why not square regions?
The reason we like the diamonds rather than square is because the spin flip identities will cover all the points. If you had a square, if you had a 3x3 square, then this point will never enter. These spin flip identities. Well, this number will never enter. They can enter, but you don't pull down the spin from the sides. I mean, we tried this square before, but it seems that it's more efficient to work with diamond. After all, you want to you want to get most out of the number of points you have, and it seems that the diamonds are the best one to use in our experience so far. Okay, so here's a table of the number of independent equations and so forth that you get. So in the 2D, so let's say in the situation of the 2D Ising model without magnetic field, of course that's a solvable theory. We know the solution, but we can compare with no solution. Without magnetic field, we can impose Z2 symmetry. If you turn on magnetic field, then we relax Z2 symmetry. There are more variables. So that's why the number of independent variables are different. So in the first column here, the numbers are what we call the primitive subsets. That is, the subset A that lies in the domain D. The domain is this 13531 diamond. So we fix that domain. One can consider all the subsets A in that domain, but the primitive subsets just enumerates the ones related, unrelated by symmetry. So of course, if it runs related by symmetry, the experience values are the same. So for example, in the case of the no magnetic field for that domain, there are 569 different moments. those are the variables that enter the spin flip identities or the Schrödinger equations. It turns out that after you analyze these equations, so how many? Well, there are a lot more equations. I didn't write we didn't list the number of equations in this table. So there are a lot of equations. But at the end of the day, you'll find that after you're solving this numerically with a sufficiently high precision, you'll find that there are 549 independent equations which determine 19 variables. The reason it's 19 not 20 is because the extreme value of 1 is just 1. So that's so one of them is just 1. So the last column, these are the numbers of independent variables that enter the SDP problem that we'll then solve. Now in 3D, the biggest region that we have considered so far is this, let me see if I have a picture. I'll show a picture of that later. So in 3D, the largest region we have considered so far is the 15551 region. So that would be like this picture I drew here, but you stack 3 more layers of these 5 points. And another one at the bottom. So this will be the 15551 region. So in this case, you end up with the 629 independent variables in the SDP problem. Okay, so here's the result of the 2D. This is the result for the 2D Ising at 0 magnetic field. So this is a solvable model, just as a test of principle. So we're considering here the 2-spin correlator at adjacent sites. So this subscript 0 and E1 is referred to the original lattice, and the first, the unit vector along the first direction. Doesn't matter. So this is the nearest spin Fourier function. It is proportional to the energy density expression value of the model. So that's the vertical axis. That's the spin correlator, the nearest sites. The horizontal axis. This is the coupling J, and the critical value is 0.44 something. This vertical line here. So this is the critical point. And the magnetic field, as I said, is set to 0 for this plot. The gray dots, these are results from the 131, the 2D 131 diamond. So for the 131 diamond, only considering 5 points, the bounds are quite weak. You can see here, but they're still non-trivial. The blue dots are the result for the 1351 diamond, so that is already kind of has the right shape. So the blue dots are the max and min bound from SDP. I should make a comment that so far, for the computational efficiency, because we have a lot of variables, it turns out, so far what we find is that we want to, the SDP software we use to obtain these results are Mosaic and SDPA QD, so quadruple double precision version of SDPA. For some of these points, the Mosaic will be sufficient. Some of these points we even get with mathematical SDP, optimization. But with higher precision, as we'll describe later, sometimes we'll need, most of the time we'll need SDPA QD, which is much slower, but it's necessary to achieve some more higher precision results. So these blue dots are the bounds obtained by imposing, I think in this case, just the reflection positivity on the 13531 diamond. As I mentioned earlier, the square positivity does not improve the bound. Just for visualization, this shaded blue region is just, it's just the region between the bounds, and the black curve is the no exact result. Now, of course, you can see here that the bound is weakest at the critical, or in the vicinity of the critical point. It's it's still visible by eye, but they become quite tight when you move away from it. we can actually compare this to, so in order to see how far the bound is actually from the exact result, you can make this plot. So in this plot is the deviation of the upper bound and lower bound versus the exact result in this 2D with no magnetic field, the exact solvable model. So the blue, so you can, going back to here, you can see that the upper bound is very tight above JC. The lower bound is very tight below JC. And so here illustrates how tight it is. So the upper bound, the deviation of upper bound between upper bound and exact result, you have sort of kind of exponential dependence when you move away from the critical coupling, and becomes tight very quickly. Not so much below JC, whereas the lower bound is deviation from the exact result, becomes tight very quickly below JC, but not so much above JC. And you can compare this to the typical precision you can achieve with Monte Carlo. So if you do the Monte Carlo with the Metropolis algorithm, the typical, like this, a million Metropolis sweeps, the 1 sigma error bar would be the size of this red curve here. And of course, that's much better than the bootstrap bound we have so far near JC, but then some of these upper or lower bounds becomes, can compete or become better than Monte Carlo a little bit away from it. Now, I should say, of course, that this Monte Carlo method we're comparing with here is the simplest thing you can do. There's probably a much more clever way to improve the precision, but just as a matter of principle, here you can already see that these bounds can sometimes compete with Monte Carlo. But in fact, the situation becomes more dramatic when you turn on magnetic field.
So what about Griffith's inequality? Are you putting this in at this stage?
I think for this, if I recall correctly, the first Griffith inequality didn't make any difference. I will discuss the role of that shortly, but I think in this case, if you put it in, it does not improve the bound.
So how do your results know that you're on an infinite lattice instead of a finite?
We have the translation invariance.
Yeah, but if you have periodic boundary condition.
For periodic boundary condition, the reflection property will fail. So in fact, we have explicitly verified in a simple example. You can check that if you just do 5 by 5 periodic lattice, you can just do the sum exactly. It's actually excluded by the bootstrap bound in some situation. Not over here because the bound is rather loose, but in the situation where the bound is tight, we actually have verified that. So the bound definitely knows about the infinite lattice. As I was saying, for the periodic lattice, it's the reflection probability that I think fails.
Can I ask, the first Griffith inequality, how does it work for zero magnetic field? Because
for zero magnetic field, it will just say that the odd number of spins is just 0. I mean, 0 is still not negative, that is compatible.
So why do we impose that in the broken phase, for instance? I mean,
sorry, why do you?
I mean, in the broken phase, you should select one of the two vectors, but it looks like this condition, it takes first the infinite volume limit. First zero magnetic field and then infinite volume limit.
I haven't discussed that yet. I will come to that on the next slide. Right? So far, it's a two-spin coordinate, so this doesn't care about that.
Yeah.
But I'll come to that. So now we're talking about yes.
Do you have some idea of how your method converges? So like, if you compare it, I guess this 131 to the 13531, like as you do more and more, like will it always keep getting better, or does it stop getting better?
I don't have any data to show you to convince you that it will get better. But the improvement from 131 to 13531, of course, is very dramatic. And
I'm just wondering, because like there's a question with the bootstrap, like does the island always get smaller, or does it just stop at some point?
Yes, that's certainly an important question. I was planning to discuss it at the end, but I might as well just say it now. I strongly suspect that the convergence would have something to do with some kind of asymptotically null eigenvector of this matrix, which will become bigger and bigger, and there should be some statement about some approximately null state. Where you take more and more, some specific combination of spins. We haven't figured out what that would be if it exists, so we're hoping to do some numerical experiment to give some hints on what this would be, because if you know what that would be, it can also potentially greatly improve the efficiency of the programming, because you will know what to look for to get the optimal balance. But that's for the next. Anyway, so here's a plot of just a single spin, just mechanization. In this case, this is still for zero magnetic field. So not surprisingly, the lower bound is actually always zero. So this plot is for the upper bound. And so this might be a little hard to see. There are 4 different things that have been plotted. The black is the exact result of the magnetization. And the symmetry breaking phase, of course, for J less greater than JC is non-zero. So here, in different shapes and color of the dots, I'm showing 4 different bounds. The one that paint, so the weakest one, these black circles, that is the bound based on reflection positivity on the 131 diamond without imposing Griffith inequality. There's already a non-trivial upper bound, but if you impose Griffith inequality, so we have 131 plus G1, this means adding first Griffith inequality, it drops down to 0 below this orange line here, it's a little hard to see, and then it agrees with that. So there's a bit of improvement. But as I said, I believe that the Griffith inequalities are not logically necessary. As you can see, when you go to the 13531 diamond, without Griffith inequality, you already get this red upper bound. So that's already converging toward the exact result. If you include the Griffith inequality, you get this blue crosses here, which improves a little bit. It becomes 0 for a bigger region, and then it rises, but it's consistent. It's a little bit tighter. Okay. All right. So let me. So now let me show the result with magnetic field. So first look at this left one. So this is.
Sorry, another quick question. Do you have some intuition? Why is it worse on the left side than the right side?
Sorry.
Why are the bounds worse on the left?
I don't have a very deep thing to say, except that this upper bound is always, as in previous case, always much tighter above JC. I'm sure there's a good explanation. In fact, I think similar thing was observed, by Zetran and Vologia in the Yang-Mills theory context. But I don't have anything very intelligent to say, but I'm sure there's some explanation.
Is there a lower bound in this case?
The lower bound is 0 in this case, but I will discuss what happens when we turn magnetic field. There's something interesting to be said. So this is still the nearest spin correlator, but now with magnetic field. When you turn on non-zero magnetic field, the model is generally not known to be exactly solvable, for good reason. In fact, even the continuum field theory, generically in the neighborhood of the critical point, when you move a little bit away from the critical coupling and the magnetic field, the general Ising field theory, even in 2D, is not an integral field theory. So there's good reason why it should not be regarded solvable. So here is a plot of the Bootstrap bound on the nearest spin correlating function as a function of h, which is this axis over here. So this is 0 magnetic field, increasing magnetic field, and this is j. And the critical coupling is somewhere around here. Now, in this plot, both the upper and lower bounds are in the plot. It's a little hard to see the difference. Now, on the edge here, when magnetic field is 0, this plot of the upper and lower bound, you can see a little bit of separation. This was the same as the plot I showed you earlier. But they quickly meet, and you will not be able to see the difference. In fact, to help you resolve that difference, which is not possible to see by eye, we're using this color scheme to represent the gap between upper and lower bound. And this is what the color scheme means. So, as you can see, this color bar here, the red is like 10 to the minus 1, so that's the visible gap here. Blue here, it's hard to read. Blue here, the deep blue is 10 to the minus 15. So actually over here, there's kind of 15 digits of agreement of upper and lower bound. So for this, we have to use the SDPA QD, like Mosaic would not be able to resolve that level of precision. But even the red, even the yellow is already 10 to the minus 6, and that is competitive against Monte Carlo for the most region of this chart. It's kind of a funny thing that this red band kind of extends away from H0, so in this direction. one might speculate that this has something to do with maybe a complex CFT like things going on here, because the bound is weak when the Gaussian length is, the bound based on some finite region is supposed to be weak when the Gaussian length is large, and maybe it's some kind of a remnant of some kind of an imprint of the existence of some complex CFT at the imaginary field.
Is that line like a real line, or is that like an artifact of the color?
This is this pixel plot is just because we have sampled only the points.
But the boundary between the red and the yellow.
That's just what it is. I mean, each of these pixel is represents the color that is the gap between max and min somewhere in the middle of let's say the midpoint of that value of J and H. Those are the points that we sampled in getting these bounds. I mean, of course, numerically, what you do is you choose some value of J and H and you submit the job to the cluster. And I should mention that with SDPA QD, in the zero magnetic field case, I should say that depending on whether magnetic field is zero or non-zero, if you impose a Z2 symmetry, in the zero magnetic field case, you have fewer variables, fewer equations, and it takes just 15 minutes to get the results. But with this plot, each point takes about 5 hours, which is still not that bad on a single core. Okay. I guess I should. Okay, so here's a more dramatic comparison of the gap of the bound against Monte Carlo at JC, but very magnetic field. So this plot on the left. This is just a slice in the picture I showed earlier. So you fix J to be JC and just go in that direction. You go in that direction. I want to see how the difference between the upper and lower bound depend on magnetic field compared to the error you can achieve with a typical Monte Carlo simulation. And you can see that the dependence is the way that the Bootstrap bound tightens is quite dramatic. Very quickly for a little bit of magnetic field, it becomes extremely tight. But just as a sanity check, because for the zero magnetic field, we don't have the exact solution, but you want to make sure that it's consistent with Monte Carlo, and indeed you can check that it's compatible with Monte Carlo at 2 sigma in this case, but not necessarily at 1 sigma. So this chart, I won't go into, it's not terribly important for now, but the point is that in this chart, if this thing below, if this bar lies below the horizontal axis, it means that the Monte Carlo is not compatible with Bootstrap bound at 1 sigma, but it's compatible, will turn out to be compatible at 2 sigma.
Is this a fair comparison in the sense that a million sweeps will take about as long to run as the positivity approach?
I think it will take actually longer, but the thing is that with with Monte Carlo, if you increase the runtime, you have the inverse square root law, right? So if you run for 100 days, you only for a little bit, like this down there, whereas the where the Bootstrap bound, of course, changes very dramatically. But of course, eventually one will hope to do better, perhaps include a bigger region. This entire, I don't know where the Bootstrap bound will get to. I mean, this is certainly very sensitive to where you are, and it's very sensitive to also the coordination network. I should say that it's not really surprising that Bootstrap bound can be extremely tight when you're far away from criticality. It just means that because the coordination length is small, the sum or path integral can localize to some finite dimensional integral or some small sum, and so it's not surprising that you get extremely tight bound. And I mean, this Monte Carlo doesn't know that. It's not doing the smartest possible thing, but it's just anyway, it's just an illustration in principle of how these things can go.
I have a question about about your comment on the extreme on how tight the bound needs to be. So when you go to H going to infinity or J going to infinity, in particular, you're going to get a perfectly ordered system. That's probably going to saturate many of these inequalities. Now I can find out vectors. So at least in that case, can you say what is like if you look at the external function that the booster spits out, do you see the null eigenvectors to be corresponding to perfectly aligned spins?
Let me be very hard to check, but I cannot give you an answer immediately. You can say check that. I don't know the answer. Okay, so this is this is a more detailed plot of the. I should have mentioned that earlier. This bound was obtained by combining the first Griffith inequality with the reflection quality. Now, if I look at a slice at the fixed h instead, so that would be I fix h, I go in that direction. So here are a couple sample values of the h, and you can see some qualitative difference. So on the left hand side, this is when h is small, 0.03. This is when h is 0.3. And the top two are still the spin nearest spin correlator. And the shaded blue region is between the upper and lower bound. So the bound is mostly very tight, except in some value of j, a little bit away from critical point. The interesting thing you notice here is that actually the lower bound is not monotonic. Now I said that the second Griffith inequality, which we haven't imposed yet, is going to tell you that these moments are going to be monotonic. So far this bound doesn't know that yet. And it's more dramatic for the single spin, the magnetization. In this case, so actually this gray dot here will be the 131 diamond. This blue is 1351. So you can see that as we increase the region, very dramatic lower bound increase from this to that. Now of course, over here, for larger j, the bound is still 0. But as you can imagine, if you increase the region, probably this bound will further converge. And so these are without, and of course on the right hand side, basically you cannot tell the difference between the upper and lower bound. So this is without imposing the second Griffith inequality. It turns out that one can explicitly verify that in this region where when lower bound is not monotonic, actually the SDP solution will explicitly violate the second Griffith inequality, which, by the way, as I mentioned, most of which cannot be imposed. At least I don't know how to impose as a positive semi-definite condition. So it's a little bit harder to impose that systematically. We did not try to do that. We can verify. This is a simple example of the 131 lower bound, where we can verify that when the lower bound is not monotonic, the second Griffith inequality actually is not obeyed for some of these moments. That information is not visible from the plot. The plot is meant to illustrate that where you have the orange points, if you look at the solution, these moments do not obey the G2, the second Griffith inequality. Here's if you care about, of course you should care about the spin correlator, the bigger, longer distance away from each other. Here's an example if they differ by two sites, so S0 and S2 E1. You get a similar bound, but it's just a bit looser. I mean, of course, for this you have to maximize or minimize this other spin correlate. And finally, this is the 3D plot. This is the last, I think this is the last plot I'll show. So in 3D, as you might imagine, you have more variables, more equations, more bigger matrices. Everything becomes a little bit harder. The gray dot here is the bound you get from the 131 diamond, which is this yellow region here, or orange, I guess, region here. The brown dots are the upper and lower bounds for the 1551 region. That is the orange together with the red. The biggest region, as I said, we have considered consists of the orange, the red, and the purple. 15551. So that gives rise to these blue dots. I should say though that in this case, SDPA QD was too slow so far, and we have not obtained a result using SDPA. Instead, we just use Mosaic. Now with Mosaic, it turns out that in this case, it cannot handle, in this case, it cannot, for the biggest region, 15551, it cannot quite handle the full matrix. The biggest, I didn't mention this earlier, but in order to get this positivity matrix, you can take advantage of the symmetries of your region and use the so-called invariant semi-definite programming, where you basically only need to pick the spin combination that's a representative of each irreducible representation of the symmetry group that's relevant. So in this case, it turns out that the biggest matrix you encounter is 2400 by 2400. For that matrix and this many variables, is in the Mosaic couldn't handle the problem, but we can truncate the matrix to a smaller kind of a principal submatrix. It's still positive semi-definite. It's not an optimal bound, but in many cases we have tested, it's close to, you get a bound of the same order as the optimal one. So this blue dot is for the biggest region, but we have truncated all the matrices to 100 by 100 matrix, and you get this blue region, which is already better than the brown. The red curve is a result of Monte Carlo. Now in this case, these bounds are not quite competitive against Monte Carlo yet, but the next step will be to try to improve the algorithm in various ways, and there's lots of room for improvement, but I'm already out of time, so over time, so I should stop here. Thank you.
You mentioned this complex magnetic field. So there is the Young fixed point.
Right.
Can you remind us, does it lie in the region with J larger than J critical and imaginary magnetic field, or with J smaller than J critical and imaginary magnetic field?
Isn't that, you're sort of exactly at JC, but you're moving infinitesimal?
Well, not exactly. You have to fine tune both, I think.
Right. True. True. But it just goes like the h to some power. I mean,
you have to. This fixed point lies at some finite value of h critical and some finite value of j. I just don't remember.
Yeah.
Where it exactly sits in your plots.
Of course, I'm not plotting imaginary magnetic field.
Yeah,
I'm
not plotting, so. It's probably a J larger than J critical, because the magnetic field has a disorder in the pattern.
Yeah, I think the other round. Brock, do you remember? I thought it should be in the high temperature phase.
Yeah, I think so.
Yeah.
Okay. So then it cannot explain this feature that you were showing.
Yeah, I mean, I don't have an actual explanation. I mean, it was just a speculation.
Questions?
Could you just explain why G2 is not a 2x2 matrix with say SB on the
right.
diagonal?
So what I'm saying here is that maybe I can write it here. If B is a G, I can write that. So that is SAG greater than or equal to SA squared. So this is equivalent to the positive definiteness of the matrix 1 SA SAG. If you replace this A by B in general, these two things are not equivalent. You know, if this matrix is not symmetric, if this relation doesn't hold, you can verify.
Okay. So the determinant would be okay, and trace if the diagonal. This was
yeah.
Fade out.
Yeah, I mean, the matrix is not symmetric. The positive definitely is not equivalent to just the principal summation spin.
But
and
if
the
you're
positive return.
isn't it still going to trace positive and determinant positive? It's just two eigenvalues, so we could check tracing determinant. And the determinant.
No, it's not enough just for the eigenvalue to be positive, right?
What can I think? I have two eigenvalues.
So it's not a symmetric matrix, so you shouldn't think in terms of value storage.
I shouldn't think it as a diagonal.
Yeah. I mean, you can write down various slightly weaker conditions that are of that form, but I don't know how to, write the general one just in terms of a single matrix being positive somewhere. Might be possible to do some relaxation, but we haven't figured out how to do this. But anyway, so far we haven't, tried too hard to put in that information.
So you said that you didn't find some relaxed form of this inequality that you could input.
That's right. We didn't find the relaxed form of this inequality.
And this special form, it's not like, can you input the special form when
Yeah, we did consider this, but it doesn't seem to do much. So, for example, in the plot I showed earlier, where we expect that this bound will probably become monotonic when we impose the second Griffith inequality, but it turns out that the ones that are violated over here by the lower bound, without this equality, are the ones that not of that form. Are the ones where we cannot phrase this as a SDP form.
Have you contemplated bootstrapping like disorder observables, like domain walls in 3D, or?
No, I mean, there are many things one can try to do, but so far we have only done the minimal things possible. There are a few kind of obvious improvements we would like to do before trying to think about other approaches. To begin with, we want to just be able to, we want to work with the most symmetric region, then we can, make the maximum use of all the symmetries of the problem. But already for the more symmetric region, it's a 1, 5, 13, 5, 1 diamond in 3D, and that's already was just a little bit out of reach with the algorithm we used, but it seems that we can improve the algorithm, and at the moment it seems to be perhaps hopeful in the foreseeable future to get that. And of course, we also want to elongate this region so we can get non-trivial bounds for a longer distance correlator. It's not clear at the moment whether it has some useful things to say about about the continuum or about the critical to connect with the CFD. And of course, one could try to imagine somehow combine this with what we know about the CFD, which is completely complementary to this. But these are all kind of things we want to. And then next steps to be taken.
I have a naive question. Would your method avoid problems with like fermions that like traditional lattice approaches have, like sign problems or something?
Are you thinking about a Hamiltonian system with a real-time evolution, or I mean, because for the statistical model, there's I'm just summing over variables. There's no.
Right.
What's the difference?
Okay, so this is a very naive question, but like I thought like in general with lattice approaches it's harder to study certain systems if they involve fermions. And I was wondering like if that you could avoid that and somehow get better results than people usually.
Okay, I guess. Okay. I think you are referring to a situation where, I mean, the sign problem is really just the sign or the phase of this weighting factor. Right? I mean, I think you're considering a situation where, for example, the imaginary magnetic field would be such an example. So if you want to probe the Liang neighborhood or the Liang singularity, things like that, we like to apply this to imaginary magnetic field, and indeed, many of the assumptions here will break down. So, because the positivity had to rethink what the positivity is for generic, if you have some generic phase here, you will not have the usual positivity. So, but to the extent you can prove, some notion of something like reflective positivity, then you can still try to play this game. I should mention, by the way, that it's quite possible that some positivity relation similar to the one described here exists for purely imaginary fields. It's something to try to play with. So far, I haven't come up with anything, but maybe there's something.
It seems that many things would change if you were to consider, for example, next to nearest neighbor interactions.
I showed a plot earlier of the next to nearest neighbor.
Interactions.
In interaction, sorry.
If you like
interaction.
next to nearest neighbor interaction.
Well, that just means that these split flip identities will spill over a bigger neighborhood. But the computation is going to be a bit more expensive. But in principle, that you can still package it in this way.
But the various positivity arguments know that.
One has to be careful in proving these positivity conditions, which are special to the model. Right? So, for example, one of the cases where I showed, you need to assume that J is a negative. So this is model dependent, I think.
And also, what about lattices of different geometry that sometimes are relevant for, say, I don't know, frustrated magnetism and things like that?
You're welcome to try. So I'm only trying the simplest things. So far, of course, those are various things that one can consider. I should mention that.
But I mean, the method. You think the method will still work for you?
To the extent that there's some positivity condition, yes. This split flip relations are very general. But the positivity it's a little trickier. But the thing is, okay, you always have the square positivity. Here, okay, I should say that reflection positivity is a bit special, but square positivity obviously always is there. Here, I didn't discuss square positivity much because it seemed to be weaker than reflection positivity, and it's always seems to be redundant. But if you didn't have reflection positivity, you would still have square positivity, and they're still non-trivial. So I don't know how much mileage you can get. For example, random lattice, you only pose a square positivity. That I don't know. But it's not like you have nothing at all. Related to this longer range coupling, I should say that one thing one could wonder, which is a bit orthogonal. Well, it's not completely unrelated to this. Is try to understand whether the bootstrap method can be useful for identifying the fixed point of the block spin transformation. So it's also kind of a it's a fixed point problem, but one may wonder whether you can put some rigorous bounds. But it's a bit orthogonal to what I've done here, but it's of a similar nature. Yeah.
Just a quick question about the numeric. You said 1,5,13,5,1 is just out of reach. What's the hard part? Is what I wanted to know.
Sorry.
What's the hard part of the computation? Is it?
I think right now the bottleneck really is just that there are a lot of variables and dimensions are big, so it's very slow with SDPA QD. It's like you take like one iteration per day, and you take like a few hundred days to get a result. But there are potentially many ways to improve. For example, you can truncate these matrices. You may not get an optimal bound, but you may still get a bound that's good enough. It's harder to truncate or restrict the number of variables. That's quite tricky. So you might say that I don't want to consider all the possible spin insertions in this region. Of course, I want to select the relevant ones. But so far, we haven't come up with a clever way to do that. So far, we just consider all the possible spin insertions. But I don't know whether there's a way to restrict the numbers, the kind of spins configuration in the region to make to still have good bounds.
So it's the number of variables after you've used up all the linear equations, or?
That's right. So in the case of this region, the 15551, after you use all the linear equations, we still have 629 independent variables.
Okay.
So if you have the bigger one, I don't know how many, but it will be at least in the thousands.
Okay,
Just one. What are these solvers that you were mentioning? I thought
so
there was SDPV and
there's Multec and there's SDPA. There are various versions with a higher precision, and we use this quadruple double precision, which has.
Why not just use STPV? I mean, what's the...
It's because it seems to be too slow for our purpose. It's just slow. These have lower precision, right? STP is arbitrary precision. These have fixed precision. So for our purpose, this SDPA QD is sufficient for our purposes. It has more than 50 digits of precision, and so
STPB is optimized for completely different type of problem.
sorry.
STPB is optimized for completely different type of problem.
So maybe my question, when should we use this? Maybe should we use this for, yeah, when should we use this other solver?
So, this problem, when it's small, you can just use Mathematica. You use like 2 lines of code, and you like some SD-definite optimization, you answer. But when you have higher precision, when the matrices are big, then the Mathematica is no longer sufficient. I don't have a very rigorous understanding of this, but my sense of the necessary precision is the following. So you have some internal precision, but then the difficulty is that these matrices can have entries of big scale separation. And for our problem, typically 10 to the 10 scale separation, and you cannot ignore the small entries. Somehow they're important. And so if you have the solver of maybe let's say 16-digit precision, if you have 10 to 10 scale separation, you lose 10 digits of precision effectively, and you only have the 6 digits that you can trust. That's our experience so far. That's a rough estimate. I don't have a rigorous understanding, but that seems to be the case.
I think if your precision fits into quadruple double, then it might be worth trying this. If your precision doesn't, the required precision is higher than that, which of course is the case for most numerical bootstrap problems, then you have SDPA GMP versus SDPB, but I would bet that SDPB is still faster, at least skills better.
Okay, thank you.
I don't know if Ying has something to add to this, because Ying has some exchange with the developer of the software.
No. Yeah, the ultimate thing would be to rewrite SDPA QD so that it still fits precision, but also has the optimizations of SDPB, but that would be a huge amount of work.
When you say optimization of SDPB, what do you mean exactly?
SDPB is optimized to work with this polynomial positive matrices, which have special matrix structure.
Yeah, so here we don't have any, we don't have this variable in the usual Bootstrap where it's it's just a fixed matrix. Whose the entries are.
It's a fixed and it's a dense matrix. It's not.
That's right. It's also dense after you solve these. That's right.
I mean, that's a degree 0 polynomial matrix.
Yes. I mean, of course, you could use SDPB, just it seems to be not very efficient.
Let me add something non-trivial, which is that I asked David, and I think it's not entirely clear that SDPB is less efficient for degree 0 polynomial matrices than SDPA GMP.
No, it definitely is more efficient. It's like what we were using for our integrated constraint bootstrap was SVB, and those are also just constant constraints. But SVB was much faster than the other things we use.
Really? Okay, maybe we have not optimized parameters. We'll be interested to discuss it.
Well, hence my earlier point that if you have quadruple double precision, you're good. But otherwise, if you move to arbitrary precision, then I think SDPB is your best bet.
Well, so far quadruple double is a little bit more than necessary, but it certainly seems to be good enough for the purpose so far. But it will depend on what in the end what is the precise object.
Okay.